I guess we stopped last time where I was giving you the definition of E. And so, again, E is just some number, which can be defined in several ways. And so it's just a number. Let's do, um, let's say, on page 543, let's do problem number, let's say 24. And so I want to graph f of x equals e to the 2x. And so let's write this as y equals e to the 2x. And I'll just use the properties of exponents. And so I'll write it as e squared to the power x. Well, since e squared is greater than 1, then it will look like uh, a graph that's growing exponentially. And, well, actually, let's also find, I guess, the since the base is greater than 1, I guess, and it's just a base to the x, then the y-intercept is the 0.01, and the horizontal asymptote is just y equals 0, the line y equals 0. And so I can sketch the graph of this. Well, it just looks like some base greater than 1, and so it just grows exponentially. So this is a graph of y equaling e to the 2x. And it passes through y equal 1, and it approaches the x-axis as x goes to negative infinity. And so that really was all I wanted to talk about for section 13.1. And so let's start section 13.2, the meaning of logarithms. So let's recall that, let's say 2, 2 cubed is 8. Therefore, the exponent of 2 that yields 8 is the exponent of 3. Similarly, um, 3 to the 4th power is 81. So that says that the exponent of 3 that yields the result of 81 is the exponent of 4. And so 4 is the exponent of 3 that yields the answer 81. So let me think of this another way. So note the exponential function, f of x equaling b to the x, for sure. So a logarithm is just the exponent. And so a logarithm of some quantity is just that exponent that yields the result that you want for the given base. So 3 is the logarithm of 8 base 2. So notice that this is our base, and this is what I want to take the logarithm of. And this is my logarithm. The logarithm of this number 8 base 2 is 3. And so there is this relationship. So basically, what are logarithms? They're exponents. So a logarithm is just a notation, an idea of what it means to be an exponent. So given some base, then the logarithm of this quantity for this base is just the exponent 2, exponent 3. Oops. Sorry about that. Okay. Okay. You're welcome. Um, so note if f of x equals b to the x for b for b greater than 0 and for values of b not equal to 1, that this is 1 to 1. So this is an injective function. So that's really the reason. Well, so I always have when I talked about exponential functions, I had this restriction of talking about uh, exponential functions that had bases greater than 0 and not equal to 1, basically because I wanted an injective function. And so if you have a base that is either greater than 1 or between 0 and 1, in either case, say this is y equal b to the x, and the case b is greater than 1 or b is between 0 and 1. And so for any case here, for b greater than 0 and not equal to 1, you notice that I always pass the horizontal line test. Therefore, these functions here are 1 to 1. And so the exponential function is an injective function. And well, that means that the reason that we were talking about injective functions before is because, well, injective functions have inverses. So thus, the exponential function has an inverse function. we call this inverse function of the exponential function. Well, we call it the logarithm. The logarithmic function. So maybe I'll just say so the inverse function of the exponential function is called there. At least the English makes sense now. And so the inverse function of the exponential function is called the logarithmic function. So let me write it out more explicitly. Logarithmic function. I'll assume b here is greater than 0 and not equal to 1. And well, the reason for this is, of course, if b is equal to 1, then it's going to be a horizontal line, and so it won't be 1 to 1. And if b equals 0, it will be a horizontal line again, and so it will not be a 1 to 1 function. And if b is less than 0, well, then it's not a real function anymore. So it's not 1 to 1. So in order for it to be injective, for the exponential function to be injective, we want that the base is greater than 0, not equal to 1, in which case, of course, then it has an inverse. And so the logarithmic function g of x and I'll denote it by log base b of x. This is the inverse function of the exponential function maybe I'll call it f of x equaling b to the x. Okay, so that means thus f composed with g is the identity function, since they're inverse functions of each other, and g composed with f is the identity function. So if you recall, and I just did it a second ago, but I'll redo this. The exponential function for bases greater than 1 look like this. And so, well, we can do that trick we did before where you draw this on a piece of paper and then you flip it over and you interchange your x and your y axis. If you do that, then the logarithmic function looks as follows. So this is the graph of y equal log base b of x. Notice that, well, this intersects at 1. Therefore, interchange x and y axis. This intersects at 1. Notice that this is always decreasing. I'm talking about the logarithmic function. So maybe let me label this properties. Oh, I guess I should write them both ways. So before I do that, let me draw the exponential function where the bases are between 0 and 1. Yes. Yeah, so the figure on the right is always decreasing. Okay. So if I look at the logarithmic function, for this case, looks something like this. Y equal log base b of x, where the base is between 0 and 1. Again, it intersects at 1, so it intersects here at 1. Okay, so in either case, the logarithmic function it's always decreasing. So in either of these two cases, it's always going down. It is, oh, well, actually, the concavity changes. Either it's always concave up or always concave down. So I guess I'll just label it over here. It's concave down, concave up. Okay. There is no horizontal asymptote. But there is a vertical asymptote of x equaling 0. So that's the y-axis. And so you notice that in both cases, they're approaching the y-axis. And, well, neither of these have y-intercepts. It approaches the y-axis, but it never actually touches the y-axis. But we do have an x-intercept at 1. So that's my x-intercept. Okay, so let me give you some notation. So when Napier invented this idea of a logarithm, he was doing it because, well, he was trying to do these gigantic computations, actually looking at the position of planets and stars. And in order to do that, you had to do a lot of computations, multiplying, taking roots, dividing, etc., etc. And if you don't have a calculator, and of course, this Napier was in like 1640 or something like that when he invented these logarithms. And so, well, with you know, if you don't have a calculator available, then how else do you do huge computations? Well, he found one way of doing it nicely is using logarithms. And since our base system is base 10, then what he did is he looked at these logarithms base 10. And so the common logarithm is denoted by log, and this is just the log base 10. So if we don't have a subscript, then it's assumed to be base 10. And so, again, it's just the fact that he was using base 10 all the time because our base for our number system is base 10. Modern man uses natural logarithms. And so a natural logarithm is denoted by ln, and it's just a logarithm where the base is that number e that I have that I was talking about in the previous class, and very well that we had stopped at yesterday. Okay, so let's do on page 549. So I want to, in this case, interchange between the differing forms that I've written for my statement. And so let's do, let's say problem number, did I do that one? Let's say problem number 5. Log base 5 of 25 equals 2. In exercises 1 through 20, rewrite the logarithmic statement as an exponential statement. Okay, so I want to rewrite this this logarithmic statement here as an exponential statement. Well, what is the base? The base is 5. What is the exponent? Well, the exponent is the logarithm. And what is the result? Well, the result is the number inside the logarithm. And so this statement of the fact that log base 5 of 25 is equal to the value 2 is the same as saying that 5 squared is equal to the value 25. Let me do another example. Let's say problem number 8. Log base 2 of 1/8 is equal to -3. So in this case, the base is 2. the exponent is -3, and the result is 1/8. Let me do problem number 12. Log base 27 of 3 equals 1/3. And so let's rewrite this logarithmic form in exponential form. And so the base in this case is 27. The exponent is 1/3, and the result is 3. So the cube root of 27 is 3. Let me do problem number 22. 4 squared is 16. So in this case, I want to go in the exact opposite direction. And so I have started out with an exponential form, and then now I want to write it in a logarithmic form. And so for exercises, for exercises 34, oh, wait 1 second. For exercises 21 through 35, rewrite the exponential statement as a logarithmic statement. Okay, so let me rewrite that. And so my base is 4. My result is 16, and the exponent is 2. And so log base 4 of 16 is equal to 2 is the same as the statement 4 squared is 16. $33. Okay, let me do problem number 33. The square root of 3 is equal to 3 to the 1/2. Okay, and so the base, oh, I see, they wrote it in the opposite direction. And so before they were doing, so let me rewrite this so you can see what they're saying. 3 to the 1/2 is the square root of 3. And so the base in this case is 3. The result is radical 3. And the exponent is 1/2. And so 3 to the 1/2 equaling the square root of 3 is the same as saying the log base 3 of the square root of 3 equals 1/2. Any questions about that? Okay, good. Let me do, well, something similar. How about problem number 34? The cube root of 8 equals 2. Well, first note that the cube root is the same as an exponent of 1/3. And so the logarithm base 8 of 2 is equal to the exponent 1/3. And so the cube root of 8 equaling 2 is the same as saying log base 8 of 2 is equal to 1/3. Let me do, let's say problem number 38. G of x equals a log base 1/2 of x. And so in exercises 36 through 50, sketch the graph of the function, give the coordinates of the x-intercept, and the equation of the asymptote. Okay, so let's do that. So let me note here that the base b is 1/2, which is between 0 and 1. Therefore, the graph is going to look like, well, we just did that. And so if you look above, here. And so since the base here is between 0 and 1, then the graph of the logarithm, again, just looks like this guy reflected about the line y equal x. And so the sketch of the graph looks something like. And that's approximately what the graph looks. It's not a great graph, but and so this is the graph of y equaling the log base 1/2 of x. I noticed that, well, the graph intersects at 1. Well, actually, let me do this just sort of in general. And so to find the place of intersection where it intersects the x-axis, so to find the x-intercept, you set whatever is within the logarithm equal to 1 and solve. Well, in this case, the only thing inside the log is is x. Therefore, x is equal to 1, and so the x-intercept is at 1, 0. Let's find the vertical asymptote. To find the x-intercept, you set whatever's inside the logarithm equal to 0. And so the graph is just x equals 0. Let me show you why the x-intercept is found by setting x equal to 1. So to find the x-intercept, you set y equal to 0 and solve for x. And so 0 equals log base 1/2 of x. Therefore, well, if you rewrite this in exponential form, the base is 1/2, the exponent is 0, and the result is x. But of course, 1/2 to the 0 is just 1. So therefore, the way that you find the x-intercept is that you just set what's ever inside the logarithm equal to 1 and solve. In this case, it's just x inside the logarithm, so x equals 1. Let's do problem number 46. F of x equals log base 3 of x minus 2. And so I want to sketch a graph of y equals log base 3 of x minus 2. So this is basically just a translation. Y equaling log base 3 of x. And I'm going to be moving along the positive x-axis, again because I'm subtracting 2. And so I'm going to move 2 in the positive x direction, which is to the right. So let's sketch the graph of this. Since the base here is 3, which is greater than 1, then the sketch of the graph looks something like, oh, let's do it in red, like this. And so now let's translate this to the right by 2 units. And so the sketch of the graph should look like, well, let's move 2 units. So let's do the axis again. Maybe so this is 1, 2. And well, I'm moving 2 in the x direction, so it doesn't really change the x-axis because I'm doing it, translating it horizontally. And so now let's sketch the graph. So it should look the same, but I've just moved it over 2. And so this was at 1, and I move over 2, therefore this is at 3. And the x-axis moved over 2, so this is when x is equal to 2. And so I know the vertical axis is at 2, and the x-intercept is at 3, but let me assume I don't notice that. So let's do the x-intercept. Or maybe I do notice it, but I don't believe it. So let's do the x-intercept. And so to find the x-intercept, I set y equal to 0 and solve for x. And so let's rewrite this in exponential form. So the base is 3, the exponent is 0, and the result is x minus 2. So 3 to the 0 is 1. Add 2. And so x is equal to 3. Which is what we said. The x-intercept is at 3, 0. And so that's what it looks like here. And now let's do the vertical asymptote. So the vertical asymptote so I can find the vertical asymptote by just setting what's inside of the logarithm equal to 0. So I'll set what's inside equal to 0 and solve for x. So x is equal to 2. And that is the equation of your vertical asymptote. So, right. So for the vertical asymptote, you just set what is inside the logarithm equal to 0. For the x-intercept, you just set what it's ever inside. So this all implies you set what's ever inside equal to 1 and solve for x. And so set whatever is inside to 1, that gives you the x-intercept. To 0, that gives you the vertical asymptote. Is that clear? Okay, good. Let me do problem number 50. F of x equals -2 plus log base 3 of x minus 1. And so let's write it as y equal -2 plus log base 3 of x minus 1. So let's add 2 to both sides of my equation. And so y plus 2 equals log base 3 of x minus 1. And so I'm just going to translate y equal log base 3 of x. And it will be down to because we're adding 2, so I go 2 in the negative y direction, and write 1 because I'm subtracting 1. So I'm going in the positive x direction. Let me find the x-intercept. Well, as always, you set what's ever inside the logarithm equal to 1. Oh, except for one problem. That's 2 over there. Oh, you can't do that. Except for one problem. That'll give you 1 plus 2 is 3. That won't be an x-intercept. Okay, so let's find the x-intercept. But since this term here, since it's a translation, and this translation is up or down, it's going to change the x-intercept. So we don't have a pure horizontal translation. We have one that has a vertical component. And so let's find the x-intercept by setting y to 0 and solving for x. And so let us translate this, rewrite this in exponential form. So the base is 3 exponent is 2, result is x minus 1. And so 3 squared is 3 squared is 9. Add 1 to both sides of your equation. And so x is equal to 10. Okay. So therefore, the x-intercept is at 10, 0. Let's find the asymptote. So let's find the vertical asymptote. To find the vertical asymptote, just set whatever inside the logarithm equal to 0. Add 1 to both sides of your equation. And so x is equal to 1. That is the vertical asymptote. Okay, so let me sketch a graph here. And so we have log base 3. Maybe I'll do it over here. So we want to do translation of log base 3. Well, log base 3 looks something like this. So now I want to do a translation. So I'm going to translate, was it 2 down, 1 right? So 1 right, 2 down. So you go to the right 1 and down 2. So the sketch has got to be, oh, I'm going to the right 1. So let me redraw my y-axis. And so it should look something like this. And so it's got to approach the horizontal asymptote, x equal 1, and intersect at x equal, x equals 10. I'm sorry. Okay. So that really finishes off section 13.2. Let's see, we started at 7:30, so it's 15 minutes. So section 13.4, exponential equations. So let's do section 13.4, which is exponential equations. Okay, so let's do some examples. On page 558, let's do problem number 2. 4 to the x equals 64. So in exponential, an exponential equation is just an equation where the variable, what you want to solve for, is in the exponent. And so it's some sort of equation where I'm solving for something, but the thing that I'm solving for is an exponent of some base. Okay. So in exercises 1 through 28, solve the exponential equation by writing both sides of the equation as an exponential expression with the same base. Okay, so let's do that. And so if I look here, well, 4 cubed is 64. And so I can rewrite both of these as in exponential form. And not only that, I can rewrite this so it is an exponential form where the base is actually the same. And so this base here, 4, is the same as that base there, 4. Since the exponential function is injective, since it's 1 to 1, then that means that the only way that these can be equal is if the exponents are equal. And so my solution is x is equal to 3. Let me do problem number 12. $125 x equal 5. So let's rewrite it with the same base. Well, 5 cubed is 125 by laws of exponents. 5 cubed to the power x is the same as 5 to the 3x. If you have a base to a power raised to a power, you just keep the same base but multiply exponents, 3 times x. And so I noticed that, well, 5 is the same as 5 to the first power. Therefore, since the exponential function is injective, whenever the base is greater than 0, not equal to 1, which is this case, then since the quantities are equal and the bases are equal, then the exponents must be equal. Divide by 3. And so x is equal to 1/3. Let me do problem number 28. 5 to the x squared is equal to 25 to the power 4 minus x. So let's solve this equation here for x. And so I notice I'm going to try to rewrite these so that I have the same base. I notice that 5 squared is 25. And again, by the properties of exponents, a base to a power is just that same base to the product of 2 and 4 minus x, which would be 8 minus 2x. Distributing the 2 inside the parentheses. And so, since the exponential function is injective, then we must have that the exponents are the same. Since the exponential function is injective and since these quantities are equal and since the bases are equal, then I must have that the exponents are equal. So x squared must equal 8 minus 2x. Add 2x, subtract 8. And so I have x squared plus 2x minus 8 is 0. Let me factor. This is a nice quadratic, a monic quadratic trinomial. So I can factor it as follows. Put down an x. I have a plus, so let me bring down the plus, times minus is minus. I want two whole numbers whose product is two natural numbers, I guess, whose product is 8 and whose difference is 2. So 4 and 2. set each factor to 0 and solve for x. So by the zero factor property, x plus 4 is 0, or x minus 2 equals 0. Subtract 4 from both sides of your equation. And so x is equal to 4, or x is equal to negative 2. Oh yes, you of course can use a quadratic formula to solve this. Of course, in this particular case, a quadratic formula would be much more difficult than factoring. Factoring is always much easier than using the quadratic formula. So I always do a rule of thumb. You know, if it takes you more than 5 seconds to factor uh, this polynomial, then you should use this quadratic, and then you should use the quadratic formula. Again, you probably have a little bit longer of a criteria, so maybe if you can't factor it in 30 seconds, then you should use the quadratic formula. Okay. Um, that question. Oh, ah, funny you should ask that. Uh, but we got we got 5 minutes. So the answer is wait till Monday. So what I'm going to do is solve a whole bunch of them where I'm going to, so as a preview, I'm going to try to solve this. So where it's impossible. You can't write them with the same base. And so I will solve problems of that type, but I don't have enough time to really do that. So I'm going to actually let you guys out 5 minutes early. Oh, I see you guys are really disappointed. Okay, so I'll let you guys out 5 minutes early, and I guess I'll see you guys on Monday, unless there are some additional questions. Oh, here it is.